Hello everyone. Now in the third lecture of chemical equilibrium, a thermodynamic approach, we are going to discuss Kp in terms of number of moles. In the last lecture we have made a relationship, we have derived a relationship between Kp and Kc as well as Kp and Kx. Now this relationship Kp in terms of number of moles N is also very important. Now all the components has their respective number of moles. Suppose the product P, Q, R, they have the respective number of moles Np, Nq, Nr, etc. And the reactants A, B, C have their number of moles Na, Nb, Nc, etc. Okay, so these are the number of moles of the component gases. Now within the system you have both reactants and the products. Okay, so what is the total number of moles of the gas in the system? So it is nothing but their summation. So it is sum over N. Okay, and the summation of the number of moles of the products as well as the summation of the number of moles of the reactants. So this is the expression of sum over N. Okay, now with respect to this term you can express the mole fraction expression, okay, such as that of the reactant A, XA, that must be Na by total number of moles, such as the product P, which is the XP should have the expression Np over summation N, and so on. So this expression can be very much applied in the Kp-Kx relationship. In the Kp-Kx relationship, we know that Kp equals to Kx into P to the power delta nu, where P is the total gas of the system and delta nu is the stoichiometric difference of the reactants and the products. Okay, so the expression of Kx is written here. Okay, you know the expression. This is the expression of Kx, xp to the power p, xq to the power q, and so on, and in the denominator xa to the power a, xb to the power b, and so on, and here p to the power delta nu as usual. But these expressions of mole fraction now can be replaced with the expression of number of moles, and we have already obtained this relationship. So instead of xp we can write Np by summation of N. In case of XA we can write Na by summation of N, and the respective powers would be the number of moles of the respective components though. So this is applied for the products, and in the denominator this is applied for the reactants, and P to the power delta nu as usual. Now you can take into common this summation N term, but in its power you would have P plus Q plus R minus A minus B minus C, etc. So this is nothing but delta nu, so it can be merged with P, and whole to the power delta nu we can write here. Okay, so you have the expression of Kp in terms of number of moles of the components. So this is the expression Np to the power P, Nq to the power Q, Nr to the power R, and so on, divided by Na to the power A, Nb to the power B, Nc to the power C, and so on. And along with that you have the second term P by total number of moles whole to the power delta nu. So this expression is very much would be helpful in order to determine the effect of introduction of inert gas into a system. That time it would be very much helpful for your calculations. Okay, so that's all for this lecture. Thank you. Have a nice day.